up to now we've been looking at scattering theory, the observables that we can measure, motivating the observables we can measure. And in the last lecture we started the connection between the models we use to study the dynamics of interacting particles and the theoretical models and their solution and these observables that we've introduced to study scattering theory. So the standard caricature of scattering theory that I've been drawing is that we have some central potential in relative coordinates. Some particle representing two particles, right? Because we're in relative coordinates. You can think of this as a single particle at t minus infinity comes in, experiences the central potential, which is localized. The orbit of the particle is deviated according to its response to the central potential, and it flies off at t plus infinity. And the regime this introduces a regime of approximation when we talk about such experiments. We're interested in times that are much larger than some constant. In fact, we really are interested in times that go to infinity, plus and minus infinity. And we just throw out any information about what happened in the middle. So we only care about what happens infinitely far in the past or infinitely far in the future. We then notice that for many potentials, this interacting orbit is asymptotically approaching a free orbit, a free trajectory. And the way we implement this regime, this approximation, is we only care about how in states go to out states. So if you like, we average out, throw out, ignore, forget all the stuff that happens in the middle. And there's an operator which captures that information and nothing more, and that's the S matrix, or the S operator, right? And the S operator is typically a unitary operator on a suitable subspace of scattering states, as long as the potential obeys a series of conditions. That's and this corresponds, and this is in turn observable, yep? That's the last bit. So with a little bit of two-particle interference, you can get, or single particle interference, depending on how you want to set things up, you can observe the matrix elements of the S operator via the differential cross-section. And that's that quantity there. You can obtain it in experiments. And that's certainly something you can do with quite elementary setups and reconstruct this object. Now that's fine and good, but in physics, well, I guess in theoretical physics, we're interested in making predictions. In experimental physics, we're interested in discovering new physics. So let's just stick with the theoretical physics side of things. We want to predict the differential cross-section for some system. How would we do that? Well, we need a model. And the model we've chosen to focus on in this lecture is the absolute simplest non-trivial model that you can imagine. That's of a free particle model in relative coordinates in the presence of a relatively localized central potential. So the Hamiltonian for such a thing is pretty easy to describe. Looks like that. Now, there's a big question, right? How, knowing this Hamiltonian here, how would we ever infer the S matrix or S operator from the knowledge of the Hamiltonian? Well, it's not going to be easy because it somehow involves integrating the Schrödinger equation from minus infinity to plus infinity. And often enough, integrating the Schrödinger equation is hard for small times, let alone very large times. Nonetheless, we've built the beginnings of a connection between this operator and this operator. So I'll write up the question, how to get S from H. How are we going to do it? Well, when the potential is strong and deeply non-trivial, then you could imagine this is probably hard to do, even numerically. But we're not going to do that because typically in the physics, the situations we are interested in, the physics tends to be of the nature where V is small. So we can use a perturbation theory type argument. That's one hope to be able to get the S matrix from the free Hamiltonian. The nice thing is the S matrix, you can at least imagine what it looks like when the potential is zero. This should be easy to work out, right? If there is no central potential, what does the S matrix look like? Well, it takes in states to their out states, right? The same free in trajectory goes to the same free out trajectory. Nothing gets scattered. So whatever the effect of this potential is, if it's small enough, you might hope that it only sort of slightly perturbs in and out states. It's kind of true, but not entirely true. And it's this approach that we're taking for this lecture. There's a variational approach as well, which we will, I guess, touch on in some sense today. Now, actually getting S from H, we haven't quite got there. I mean, last lecture we introduced Green's operators, and we arrived at a formula for the matrix elements of the S operator in terms of in and out states. So I'll just remind you of that. So last lecture, this is the thing we want, right? This is what's connected to physics experiments, gives the differential cross-section. And what is this in terms of Hamiltonian quantities? Well, we get first the conservation. We get first the zero scattering event. This is when nothing happens. And then there's some perturbation, right? It's not always the case that nothing happens when you shoot something at an atom, for example. And then we get scattering events, which have this characteristic form here. Obviously, energy is conserved. We've proved that energy is conserved throughout a scattering process. And we manage to connect this with a thing called the T operator. Or off-shell T matrix. And I'll just complete the derivation we did in the last lecture, and also remind you of the definition of the T operator, the off-shell T operator. What is this T? T of Z is an operator and its matrix elements. I mean, this is just the definition of the T operator, which we introduced also in the previous lecture. The matrix elements of T are V, same as V, plus some stuff. Remember, this T operator satisfies a linear equation. And this is the linear equation that it satisfies. So if you can solve that equation for T of Z, then you have the matrix elements of T. And that's what features in this equation here. And this thing here is determined purely by, well, purely by the potential. And this is the green function here. That's the Green's operator contribution down there. So this is fantastic, right? So we've got here on one hand the differential cross-section sort of encoded in this information here. And this is equal to this expression here, T, and T in turn you can get from solving this somewhat complicated, I think it's a Volterra integral equation, which is determined purely by the potential and the free particle Hamiltonian. So this is the model, this is the observable quantity. So there's the full connection from theory to experiment in these two boards. Now today's task is to actually do something with this, because this is far too implicit to be useful. You know, super. We know the matrix elements of T are expressed in terms of some function of the matrix elements of T. That's practically a circular definition, right? We can, however, these things are not circular. This is actually, in disguise, it's basically a generalized eigenvalue problem for T. If you solve this generalized eigenvalue problem for T, then you know what T is. We have to find T. So today's task is T. And we're going to get at this by perturbation theory is our approach for today. Now the clue is that we have this eigenvalue type problem for t of z, and we're going to exploit the fact that v is small, and we're going to solve this by iteration. So recall so usually everything you know you do with operators, differential operators, has a finite matrix analog. So the things you can say about differential operators are that they are like matrices, they obey many of the they have many of the properties that matrices have, but also they are more pathological objects. So some of the things you thought were true aren't true for differential operators. So if you have a matrix equation, let's say it's of the form x equals a plus bx, and you want to know what x is. Given a and b, then there's a bunch of things you can do. One of them is you can just divide out by b, and then you'll get x. Let's have a look. Okay. I've just rearranged the equation. I've subtracted bx from both sides, so that's the same matrix equation here. What's x? Well, everyone knows what x is, right? You just divide by the inverse. Okay, great. So if you can invert this guy, then x, you know what x is. And actually, that's what everyone wants to do. That's all we want to do in scattering theory, is to invert b, or more particularly identity minus b. That's the whole game. And if we look up here, we can see that identity minus b is this v times g. So we have to somehow get that inverse to work. Of course, this is very difficult, even for d by d matrices, or n by n matrices. If you put this in a computer, this is sort of, roughly speaking, order n cubed arithmetic operations that you have to do, and that's just for finite dimensional matrices. What about for infinite dimensional ones? Well, then that's bad, right? We haven't got much of a hope there of doing that in finite time on a computer. So one thing we can do, of course, is if b is small, if the norm of b is small, then we can expand this in a series. So if the eigenvalues of b are very, 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 very small relative to the entries of the identity matrix, then we know that there's a Taylor series for this object here in the eigenbasis. And let's just exploit that Taylor series. So the way you would typically do this is you pretend that this is just a number, and you use the functional calculus to get the Taylor series. And if you're unhappy with that, then just go to the eigenbasis of b. Assume b is Hermitian just for the sake of this illustration, and then work in the eigenbasis, and then use the standard expansion for the 1 on 1 minus x. So if I recall correctly, the expansion for 1 on 1 minus x is something like 1 plus x squared plus x cubed plus x. Or is it there a plus or minus? I can never remember this. Wait on. I'm going to do a quick calculation up here. Let's see, is that correct? Well, you multiply both sides by 1 minus x. And then you subtract off x. yeah. So 1 on 1 minus x indeed equals, has this expansion here for x. It's very small. So we can simply substitute in that expansion here. And that indeed is one way to get at our answer, right? So this, if you just sort of truncate after some number of steps, then you're going to have an answer to what is x. And that's exactly what we're going to do today, right? Today is no exception. We're going to do this very straightforward piece of Taylor series arithmetic to work out an approximation to x. And what is x for us? X is t of z. What is a for us? A is none other than the potential. And what is b? B is, well, let's just write this in here. So a is b, and b is Vg. And that's all we're going to do. Today's job is that. So it's really nice. I mean, once you get something down to an algorithm like that, then you can start doing the real physics, right? You can get some real numbers out. Now, it's not sort of so completely trivial as I've made out. And to make our life a little bit easier, we're going to introduce some new improper states. This is important. So if you take a momentum improper eigenstate and you apply a Miller operator to it, you can get something else. Let's call that something else p plus minus. I'm going to draw you a schematic of what one of these things looks like, although my picture is going to be not perfect. Not perfect by a long way, but I hope to at least give you a feeling for what this wave function looks like, the wave function of this improper improper state. Well, I'm not going to draw that just yet. Let's just draw a momentum improper eigenstate. What does it look like? Let's just focus, say, on the real part. It doesn't really matter. So we know what these things look like. They look like waves, yeah? That's what a improper momentum eigenstate looks like. And let's just put this is like x, and this is x equals 0. So what does one of these guys look like? Well, I'll give you a schematic, right? This is by far not the most correct picture you're ever going to see. But just to give you a feeling, sort of far away, it's going to look like a momentum improper eigenstate. Somewhere in the middle here, it does something weird. And then, oh, yeah. Okay. So far away, it looks like a improper momentum eigenstate. Close to the center of the scattering potential, something weird happens. And then far away, it's again like one of these. There's also a phase shift usually, but I didn't quite get that to work in this picture. Try again, okay? So somehow the peaks and troughs are shifted relative to their free counterpart. So that's the picture you should have in mind for one of these things. And in 2 dimensions, the pictures are a little bit, well, they're analogous, right? So in 2 dimensions, you've got something that looks like plane waves. the wave function of this improper state here looks like a plane wave, and superimposed on it is some circular waves which decay, or not, depending on the potential. So that's the picture to have in mind for these improper vectors p plus minus. And the reason we introduce them is because they make our life a lot easier when we start doing calculations. So why would we introduce them? Well, we can expand full orbits, not asymptotic orbits, we can expand full orbits in terms of these p plus minuses. And that's not very difficult. You just use the definition of the Miller operator and the fact that the improper momentum states are a complete basis. Right, step one. Step two is to put this thing past the integral. Okay, that wasn't so hard. So these things are pretty powerful. I mean, if you knew them, then you'd actually know the full orbit. These things are good, right? Because these coefficients here are easy. They're just the coefficients of your wave function in terms of the free asymptotic in state. And then if you wanted to find out the full orbit, all you'd have to do is just exchange these p's with these p pluses. So finding these p pluses is a good thing. We want to do this. And the goodness continues because these p plus minus improper states are also, they have nice energy. The energy is a good, easy to calculate thing. So these things are called stationary scattering states. I don't think I said that yet. So let's make a claim about these things. It turns out that they're improper eigenstates of the full Hamiltonian. And we even know their eigenvalue. It's E of p squared on 2m. It's pretty good. Let's prove this. Well, the proof is really a one-liner. You use the intertwining relation for the Miller operator and the Hamiltonian, and then you're already done. So they satisfy the time-independent Schrödinger equation for H, these stationary scattering states. And since we have some practice at working out solutions of the time-independent Schrödinger equation, then we're getting somewhere. what's the interpretation of these things? Well, now we've got to be a little bit careful. They're not vectors in Hilbert space, these p plus minuses, so we have to be appropriately cautious when we try and work with these things, unless we say, because we can end up saying very stupid and wrong things. Now let's say something that we're pretty sure is correct to begin with. Start with a statement that is safe. If we have an appropriately well-behaved initial state, phi, in the free theory, and an appropriately well-behaved initial state phi plus in the interacting theory, then this is the asymptote of the actual orbit blah as t goes to minus infinity. That's just the definition of the Miller operator. And the mathematical statement is one of limits this vector in Hilbert space tends to this vector in Hilbert space for all, and here's the key word, proper phi, all well-behaved initial functions phi, like Gaussians and other such differentiable smooth things. This is true. However, be careful. There's a big warning about stationary scattering states. If you take this equation and expand phi in terms of stationary scattering states, just according to that formula there, you might be tempted to infer something else, and that something else would be wrong. You might think, well, it doesn't, but you might think that u of t on p plus, for example, you know, if I just replace this with p, what's stopping me doing that? Nothing. You might think that that tends, as t tends to minus infinity. Well, actually, before we even do that, we know something really cool, right? We know that that's an eigenstate of the full Hamiltonian. So we actually know what this number is, e to the minus I EP on t, p plus, right? We proved that. So you might think that this statement here implies that this tends, as t tends to minus infinity, to e to the minus I e p t of p, which has another name, which is u naught t of p. And I've said it often enough, but it does not do this. This is true, this is not a true statement there. And I'll try and give you some intuition for why it's not true in a second. So there's various ways to see that this statement is clearly nonsense, and it can't possibly be true. So this is true. This is false on many levels. So on a purely mathematical level, it's false simply because they're not elements of the Hilbert space. So in what sense can they be said to be tending to each other? Okay, that's a kind of shuts it down mathematically, but you might think that physically there's still something left. But even physically, you can quickly imagine why this doesn't work. So let's just look at water waves as a good analogy. So you have a pond, an infinite pond, and then you make some disturbance in the pond. So you have the surface of the water gets perturbed somehow, maybe the ground underneath the pond lifted up suddenly. And then as time passes, this blob propagates according to the wave equation, which is none other than the Schrödinger equation essentially, and this blob travels apart. It splits into two parts that fly apart at some velocity, and in some finite time, eventually the profile becomes flat in any finite region in the middle of the pond. Right? The disturbance just flows away to infinity. Now, we can, of course, expand this thing here in terms of Fourier waves, which are infinitely extended. Every one of these Fourier waves that this is a linear combination of persists all the way to spatial infinity and spatial negative infinity. And each of these is indeed a solution of the wave equation, or think of a piece of string as well. There's no difference between thinking of a string or the surface of water. There's both the wave equation that they satisfy, and these Fourier waves, each of them individually, are infinitely extended, and they're solutions to the wave equation, meaning that they just acquire a phase as time passes, but they're still infinitely extended. So the statement that the solution here in a finite time becomes the statement here that the initial profile propagates out to infinity and then tends back to zero in the middle isn't true for any single one of these components, right? Because they're always there. It's just that because of constructive and destructive interference, that the phases that you acquire as time passes conspire to make these kind of statements true. So statements about smooth solutions don't always transfer to Fourier components, and the intuition you can take away here is that on a simple level, that's simply because these are just extended to spatial infinity. It's one possible way of physically concluding that statements like this are unlikely to be true. So the way to interpret that is to say that any statement of this form is only true when smeared against smooth wave functions. And I'll write that out. And mathematically, this is a consequence of something called the Riemann-Lebesgue lemma, or of the proof technique you use to prove the Riemann-Lebesgue lemma. So see also So be careful, right? This is just a warning. These two boards here. Don't take some of these things too literally. This is the standing message I've been sending in the past half of this course, is that whenever you see something involving an improper state, always interpret any statement regarding it as being only true when smeared against smooth or proper wave functions. So even though it's quite hazardous to work with these p plus and minuses, we still will work with them because they're useful. You know, sometimes the gain is just simply is better than the loss. Now, I want you to recall something we said about asymptotic completeness. These p's provide a complete basis for our Hilbert space H. But these p plus minuses do not, in general, because of the existence of bound states. But we assumed right from the outset that these Müller operators take our full Hilbert space to some subspace R, we assume that, and that means that these p plus minuses will at least give us a basis for R. That's the conclusion we draw from our assumption. So there's a missing part of Hilbert space in general when you have bound states. These p plus minuses don't give you all of Hilbert space. There are some initial states which never ever can be expressed in terms of p plus minus. And they are exactly the bound states in our asymptotically complete scenario. Now, of course, this wouldn't make sense in finite dimensional Hilbert spaces. If you had an isometry that takes a basis for a Hilbert space to some other subspace, then that other subspace would already be forced to be the full Hilbert space. There's nowhere in a finite dimensional space for a basis vector to go. So this can only happen in infinite dimensional Hilbert spaces. And it's just a Hilbert's hotel type thing. You can imagine each of these improper eigenstates P as being in a room in Hilbert's hotel. Then along comes the isometry omega and moves all of them to the right, and then there's an empty room. And that's perfectly consistent with omega being an isometry. Oops. So let's have a look at the overlap between two of these p plus minuses. What can we say about these guys? Well, because omega is an isometry, of course, we can say this. Which means they're a nice improper basis for R. Now, we assumed that our Hilbert space is spanned by scattering states and bound states and nothing else. None of these weird in-spiraling, out-spiraling, strange, exotic orbits. And that means that we can express any vector in this Hilbert space in terms of a linear combination of scattering states, which are these p plus minus stationary scattering states, and whatever some basis for b. And that means we have a completeness relation that we can write schematically. That's just a completeness relation now in terms of our new basis. Okay, all very well and good. Now we have these stationary scattering states. They look pretty useful, but we don't have an equation for them yet. Let's try and get some expression for p plus or minus so we can actually use them in some calculation. We've already derived something that implicitly tells us an equation for stationary scattering vectors and states, and that's this Müller operator and how it's expressed in terms of the Hamiltonian. This is something we derived in the past 2 lectures. And by expanding phi in terms of p's, we're going to arrive at an equation for p plus and p minus. Oh, I need a minus sign there. And this is a 0, not an I subscript naught. I times by 0. you just expand in terms of p's, and then we'll take off the phi of p. So expressing this equation for phi plus minus in terms of phi's of p's, well, we see that on the left-hand side and the right-hand side, we have this formula that recurs. So hitting that with a completeness relation, if you like, will allow us to conclude, oops, I've forgotten something, haven't I? Given that P is an orthonormal basis, albeit improper, then this equation has to be true, right, for every for all phi of P's, for every one of these coefficients. So we can just remove the coefficients. And this is the equation that we might conclude from that line of argument. There it is there. Now, we've been warned multiple times that this might warrant some care. This is no exception. This is true only when smeared against proper functions. Now this is sort of halfway to getting the t operator. If you like, this is the t operator is somehow the bracket version of this equation. So if you like, this is the expression of the Miller operator in terms of our improper scattering states. And the Miller operator is half of a scattering process, right? It takes you from an in state to like the full trajectory, but then it doesn't take you out again. You have to get out. And so to get out, then we need the T operator or the S matrix, depending on how much work we want to do. And then we use this equation twice, so to speak. once in and once out. Now remember, we had an equation for the t operator. We derived a couple of, I think, last lecture. And it's this one, determined purely by the Hamiltonian of the model. There it is there. That's how the t operator acts on a improper eigenstate P. And then by looking at this equation above, we're going to work out how to express t in terms of these p plus minuses, right? So if you look down here, we've got this GVP. And GVP, that appears here. So GVP can be expressed in terms of p and p plus minus. And that gives our first equation that we need. Let's call it I. A very lovely compact equation. There it is there. T on an asymptotic in improper state P just gives you V applied to the P plus minus. And that in turn tells us what the T matrix is. What is the T matrix? This is the thing that's most intimately connected with the differential cross-section. What is this? Once we know that, well, we look up here. This thing is just P prime on that times P. Here comes the really crucial formula, right? P goes to P prime. That means I just have to apply a P prime here. And then, boom, I now have an equation for this object. It's almost as compact as you could ever hope for. I mean, of course, there's no such thing as a free lunch. I mean, this bit's easy, but that bit's still not easy, right? We've still got something to do. Now, we can do, we can take daggers and look at the bra version of this equation. And that gives us another formula for the T matrix, which is that. So we have these two formulae for the T matrix. Call that 2. And the remaining task is to somehow, I mean, if we could somehow work out P plus minus, then we'd be done. We'd have a full dynamical connection between the differential cross-section and the Hamiltonian. So we're obviously going to have to give up on knowing what P plus minus is analytically, but we might be able to approximate it. And that approximation is what we'll spend the next board doing, and is what will give us our main calculational tool for calculating differential cross-sections. Now remember, we can always intertwine G naught V and GV and G naught T. That also comes from the definition of T, and that allows us to derive what you might call the Lippmann-Schwinger equation. Yup.
I think the prime in the equation I has to be on the P and not on the
All right. So you think the prime in equation 2 needs to be on here and not P minus? Is that?
I think so. Because we just stagger
Oh yeah, that does look a bit odd, doesn't it? What if I do this, right? I think I was missing a prime off that P. I think that's it. Yeah. So we're almost done with our quest to connect the differential cross-section to something we can calculate. We've understood that I and II are the most direct means of getting the differential cross-section from P minus or P plus. And, well, this one here. So let's go ahead and try and calculate P plus. We can't, of course, because it's too hard. But remember what I told you about equations that look like this. The way to work out what P plus minus is you subtract G naught V, P plus minus from both sides, and then invert, and then derive a Taylor series. So we're going to do exactly that right now. And that series has a name. It's called the Born series. And it looks like that. That's what you get from subtracting G naught V, P plus minus on both sides, and then inverting G naught V, or identity minus G naught V. I'll write that step out just so it's completely clear. Okay, that's just rewriting this Lippmann-Schwinger equation. And then now we know that all we have to do is invert this operator to get an expression for P plus minus. And then if we just call this whatever B, this equals P plus BP plus B squared P plus dot 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 dot. Of course, that's only valid if B is small, which we're going to obviously assume. And there we have an expression for P plus minus in terms of objects that we know how to calculate. So that's this series here. And if we combine with 1, then we're actually going to get a very, very compact expression now for the T matrix. And when you combine it with 1, we get something called the Born approximation. Yep.
Instead of the V, must there be a T?
Instead of the V, must there be a T? I don't think so. Are you talking about in this equation?
No, just because I think because we said we would replace GV
With G naught T. Oh. That would be confusing. That's true, I did say that. Yeah. That's absolutely right. Thank you. Indeed, that should be a T. Luckily, it doesn't change this line. Oh, hang on. No, okay. We know that T times P is V times P plus. So, what I'll do is I'll recap some of the equations. So firstly, I'll just delete that again. Apologize. And then we'll see why that is indeed a V. Okay, so that's gone, right? And let's see what the correct equation is. So we're going to use 1. So this is aside. So let's write out 1 again. 1 says that T of EP plus minus I naught on P equals VP plus minus. So that's an equation that we trust, I hope. Then we have an equation for P plus minus. Like this. Let's see if that fixes it. And we know that that's G naught T. Not P plus minus, sorry. P. Okay, but now we use the equation here, which is 1. In here, and then that becomes the equation that I wrote down here. So I do believe it's a V, but that's a good question because So we have this expression now for the T matrix. It's a power series in V. V gets higher and V appears with higher and higher powers, but V is small, so we think that this thing converges. And taking the first term, so just the leading order, gives us an approximation for this T matrix and it's this approximation that's called the Born approximation. And that, I hope you agree, is as compact and useful a formula as you could ever hope to get. So P is an improper momentum state of the free system. V is the potential. P prime is another improper momentum state of the free system. And it's just a matrix element. Right. We could think of doing an example just to gain some intuition, and I will attempt an example, but I must warn you, I'm going to make this example up as I go along, so it's highly likely to have mistakes. Furthermore, this example will violate the assumptions that we've been working with throughout, so I'm going to choose a potential which is, I don't think it satisfies the assumptions we've been making throughout, but hey, it's physics, right? We can use this as a first approximation and see if it agrees, if the calculation agrees with what we think we'll see in an experiment. So how am I going to violate the assumptions? Well, first we're going to work in 1D. Why not, right? And then the potential, let's just make it e to the minus lambda mod x. It's not even differentiable at the origin. It's got a bound state, that's for sure. It's got 1, I think, if I remember correctly. And let's just look at the Born approximation. What does the Born approximation look like for this potential here? Even though we've violated the assumptions that we've been working with the whole way through. I mean, there's some guiding intuition to be gained from this. Well, what do we know? We know that momentum has to be conserved. So that already should tell you a little bit, right? So we have to work out this matrix element there. And this matrix element is e to the plus I p prime x, e to the minus lambda x, e to the minus I p x. And there's some factors of 2 pi that I believe are there. And this is an integral you can actually work out. been a while since I've done these Fourier integrals, so I may make a mistake here. So it's just an exponential integral that we have to do here. We know how to do those. So when x is infinity, this is 0. When x is 0, this is just minus 1 on I p prime minus p minus lambda. And then when x is 0, this is just 1 on I p prime minus p plus lambda. And when x is minus infinity, this vanishes to 0. So that's the Born approximation. Now remember, momentum has to be conserved, right? So p prime actually equals p. Or energy has to be conserved, but that means momentum is conserved. And then we shall arrive at our final formula, which I have to do it the slow way. I was going to try and do this in my head, but it won't work. There, that fixes it. And now this cancels, this, and this. And when p prime equals p, we just get the answer 2 on lambda for the differential, for the t matrix. All right, I think I'll stop here for today. Yeah, seems like a good time. And next lecture, we'll look at the structure of these stationary scattering functions, these vectors. What do they look like? What's their spatial structure? I drew this caricature of waves infinitely far at spatial infinity with a superimposed kind of disturbance. We'll go to some way towards justifying that caricature in the next lecture. So, all right, I thank you very much for your attention. See you next week.